Now we will see what is a specific heat. What is specific heat of a gas? Specific heat is simply defined of a substance is simply defined as amount of heat required to raise temperature of a substance of 1 degree, temperature of 1 kilogram of substance by 1 degree Celsius. Okay, amount of heat required to raise the temperature of a pure substance per degree Celsius per kilogram. This is defined as specific heat. So if you supply heat, 1 kilogram of a substance to raise the temperature by 1 degree Celsius, then this is how you calculate the specific heat. This specific heat C, this is the specific heat C, is equal to Q divided by M into delta T. Q divided by M into delta T. Right. So this is how you define specific heat. But see, this is specific heat you can calculate for solid, liquid, and gas. Okay, will be different. But for gas, you have two specific heat. For liquid and solid, you have only one specific heat, because in gas you have two specific heat. Let us see. One is the specific heat at constant volume, and there is the specific heat at constant pressure. Because if you take, here you can see a piston cylinder assembly in which there is gas. Initially the piston is fixed, so you have a gas here. When you supply heat, what happens is that since the piston is fixed, when you supply the heat, the temperature of the gas increases. Okay, that means internal energy of the gas increases. In a manner, you can say the pressure also get increased, because the molecules will move faster. It will hit collide against the wall with a higher velocity. So that means it will have more momentum. So the pressure increases. That means internal energy also increases. We have defined specific heat as amount of heat required to raise the temperature by 1 degree Celsius. Okay. See, when internal energy increases, temperature also rises. So you can see that when you supply heat, if you supply heat, part of it will be used to raise the internal energy of the gas, and part of it will be used to do work. Do work means to push the piston up. If you push the piston up, you are transferring an energy through work. But in this case, it is fixed, so this will be 0. So you can see that this is next hand differential. dq is equal to du plus dw. But here, see, dq is actually equal to, see, suppose this piston moves, then it will be du plus p dv, p into dv. We are assuming the piston is moving, and this we have already seen. This is called displacement work. It is a type of work. Okay, this is so if the piston is not moving, then this will be 0. So this will be 0. So that means dq is equal to du. So that means whatever you heat, supply heat, that is at a constant volume, because this is a constant volume. Since it is more moving, it is constant volume. This is used to increase the internal energy, delta U, at a constant volume. So Cv is equal to Qv by M into delta T. That is, this is a specific heat at a constant volume. This is called Cv at constant volume. This is Qv, that is heat supplied at constant volume, divided by mass into delta T. Okay, this is how you define the specific heat at constant volume. Okay, and you can write Qv is equal to integral T1 T2 mCv dt. So this is the formula we will use to calculate the heat supplied at constant volume, and Cv is the specific heat. Now let us understand what is the specific heat at constant pressure. Here also you are taking a piston cylinder assembly inside which you have a gas. So you have a gas here, you are supplying heat here. Then that means initially its volume is V1. So when you supply the heat, so its volume increases by V2. See, since the volume increases, the pressure will remain constant. That is, P is equal to constant. Pressure will be constant. So that means, see, initially the molecule, so it occupies a larger volume. Pressure will become, though pressure increases initially, it will come down. So pressure will remain constant. So if you are not allowing the piston to move, that means pressure will rise up. Okay. Now, again we will use the formula Q is equal to delta U plus W. So that means dQ is equal to du plus dW. So part of it used to raise the internal energy du, and part of it will be used to raise the work dW. So dQ is equal to du plus pdV. So dQ is equal to mcv dt plus pdV. Right? Uh, See, du can be written as, see, we have used that formula for change in internal energy is mcv dt. That is, Cv is the specific heat at constant volume plus pdv. That's the work transfer. So dq is equal to mcv dt plus, see, this is, you are here, you are using the ideal gas equation. That is, pv is equal to mrt. This is the ideal gas equation. So pdv is equal to mr dt. That means we are assuming pressure to be constant. If we are taking pressure to be constant, pdv is equal to mr dt. So dq is equal to mcv plus r into dt. And this m dq is equal to mcp dt. Okay, this is the specific heat at constant pressure. Okay, so here, okay, this is the specific heat at constant pressure. So Cp is equal to Cvr. That means, see, simply means you can heat the gas at constant volume, also constant pressure. So amount of heat required to raise the temperature by 1 degree Celsius per kilogram is different for when you heat the gas at constant volume or constant pressure. Okay, right? At constant pressure, you need more energy. Okay, here you need only, if you only QV, here you need QP. It needs more heat to raise the temperature by 1 degree Celsius. So let us make a comparison between CV and CP. So this is a piston cylinder assembly inside which you have a gas. So when you supply initially it as 100 kilojoule, it is supplied here. Here you supply 150 kilojoule. Here, see, this wall of heat is transferred as internal energy. That is, change in internal energy 100 kilojoule and temperature rises. But here, if out of this 150, 100 kilojoule is raised to raise the internal energy, and rest 50 kilojoule is transferred to outside as work. Okay, that means out of 150, you only 100 kilojoule is raised to increase the internal energy. See, temperature rise is solely due to the rise in internal energy. Okay, see, that means, see, if you have achieved 2 degrees Celsius here, here also, since internal energy rises by 100 kilojoule, you have achieved 2 degrees Celsius. But you can see that during constant pressure heating, you need to supply 150 kilojoule. During constant volume heating, you need to supply 100 kilojoule. Okay, that is why this Cp is greater than C. See, Cp means amount of heat supplied per unit mass per delta T at constant pressure. This will be greater than QV by M into delta T, because you can easily observe that QP is 150 here and QV is 100, only 100. So this is the difference between CV and CP. For an ideal gas, CP is equal to CV plus R. This is the formula connecting these two. So in another way, you can write the CV is equal to dou Q by dou T at constant volume, and then you have Cp is equal to dou Q by dou T at constant pressure. So this is another formula you can use per unit mass. This is for unit